Hi there, Mr. Sutton here, bringing you the AB Calculus 610 Extra Practice Number 2 solutions on rate in, rate out. For this problem, we have the number of people entering a museum being modeled by the F function, and the number of people who have left since it opened on the same day is the G function. They didn't tell us F or G, but they gave us F prime and G prime, which are these crazy functions you see here. We want to know at what time between 1 and 11 is the number of people in the museum at a maximum. So however you want to figure this out, we're going to need to figure out a function that kind of incorporates both of these quantities. So let's talk about the overall number of people, specifically the rate at which that number of people is changing. So if P denotes the number of people in the museum at any given time, the change in that, P prime, is going to be the rate at which people are coming in minus the rate at which people are going out. So F prime minus G prime. So now that we've defined that, we can do a few things with P prime of T. Specifically, we want to find some critical values. There's a few ways you could figure out when the number of people of museums is at a maximum. Since they gave us a closed interval, we could use the candidates test. But before we do that, we should probably see how many critical values there are, just to see if we can do this with just the lonely critical value theorem. So let's go ahead and graph this out on our calculator. So here's what I've got on my calculator so far. Off camera, I entered the F prime function in y1 in my y equals, and G prime I entered in y2. So for P prime now, I'm going to put that in y3. That's going to be F prime minus G prime. So I'm going to do alpha trace, pull up y1, and from that I am going to subtract, let me do alpha trace again and get y2. There we go, y1 minus y2, F prime minus G prime. And I'm going to graph this thing. Now in order to graph it, I only want to see P prime. I don't want to graph F prime and G prime, so let me just deselect those. And I also need a window to graph this on, so let me choose my window here. Now they said these two functions, F and G prime, are only valid between 1 and 11. Or actually, they want to know at what time between 1 and 11 the number of people is at a max. So let me just do my window to be from x min 1 to x max 11. And let me do zoom 0, zoom fit, and let's watch the magic. Grab some popcorn. All right, so here is P prime chugging along here. Our calculator is doing a lot of work to calculate this, and we notice that we are crossing the x-axis. We have a critical value right about here. So let's figure out exactly what that is. So let's see here. We've got second trace, option 2 for zeros. Let's move a little closer. Let me press enter once to the left of that intersection and cross the x-axis once to the right, and then press enter a third time to come up with the value about 7.888. So there's P prime changes positive to negative, I notice, specifically at that value of or T equals, in this case, 7.888. So that means that we at least have a local max at that value. Now, it's worth noting that this is the only critical value on this closed interval. Since that is the only critical value for this function, this implies that P has its absolute max at time 7.888. So that's going to be choice B. For this free response problem, calculator-based, we have fish entering a lake modeled by this E function right here. And fish, of course, are leaving the lake at a rate modeled by the L function over here. And these are both measured in fish per hour. And this is hours since midnight. So for our first task, we want to know how many fish enter this lake over the 5-hour period from midnight. So in order to do this, since I already have the rate at which the number of fish entering is changing, I just need to integrate E of t from 0 to 5, and that'll give me the total number of fish who enter. So I have the integral then from 0 to 5 of E of t dt. And since I don't really care how many fish are leaving, just the total number entering, regardless of how many leave, this is all I'm going to need on this problem. I just have to do it on the calculator now. So here I am on my calculator, In my y1 and y equals, I've actually entered the e of t function in there just to make my life a little bit easier. And I didn't need it for this problem, this part of the problem, but I entered L of t in y2 just because I'm pretty sure I'm going to need this down the road as well. So hey, while I'm in here, might as well get multiple things done. So now quitting out of there, I'm just going to do math 9 and get the integral from 0 to 5 because we are only concerned about the first 5 hours. We want e of t, so that's going to be alpha trace y1. That's where I stored e of t in my calculator. Dx. And press enter. This comes out to 153. Now they wanted us to round this to the nearest whole number, so this is 153 fish. For this next part, they want to know the average number of fish leaving the lake per hour over the 5-year period from 0 to 5. So for that, we need an average value kind of setup. We need 1 over the interval length times the integral of the function we're averaging. So that's going to be 1 over 5 minus 0 times the integral from 0 to 5 of the L of t function, L of t dt. This will tell us the average rate of leaving for the fish. And now that I've got this written down, all I have to do is go do it on the calculator. So here's my setup so far on the calculator. I have 1 over 5 times the integral from 0 to 5. And now I want L of t. Now remember that I stored L of t in my y2 in my y equals. So let me do alpha trace y2. And I did this when I was doing part A. I didn't need it at the time, but now I need it, and I'm glad I stored it in y2. So that's going to be a dx there now. And pressing enter, we've got 6.059, and that is going to be in units of fish per hour. On this part of the problem, we want to know at what time between 0 and 8 is the greatest number of fish in the lake. So to talk about this, we need to talk about an overall function for the rate at which the number of fish in the lake is changing. This is going to be a combination of the rate coming in and the rate going out specifically, and I'm going to define this as the f of t function. We can say f of t, the rate at which fish is changing, is going to be e of t minus L of t, rate in minus rate out. So in order to figure out where the number of fish is maximized, I need to figure out where basically the derivative of the number of fish, f of t, has a value of 0. At least I need to get some critical values. And there's a lot of ways I could go once I get those critical values. I could come up with a function to tell me how many fish are in the lake overall, and then use the candidates test. Or if there's only one critical value, I can do a little reasoning around that. Since I only need to know the time, I've got a lot of options here. So let me go ahead and graph this out. So I'm back in my y equals for this one. And again, I put my e of t function as y1, L of t was y2. So I've defined a third function, y3. This is my f of t function here. This is e of t minus L of t, y1 minus y2. And notice that I've only got this selected. I went through and pressed enter on these equals to deselect e of t and f of t because I don't really want to graph those other functions. I just want to graph this combined function. And I want to graph it on the interval from 0 to 8. So let me go to Window, and notice I've entered in 0 and 8 as my x, min, and max. Now let me do zoom 0, zoom fit, and let's take a look at what the overall rate of change of fish is doing. So this is f of t that we're graphing out. And I'm going to be looking for places where this crosses the x-axis. So there's one spot right there, and it looks like there's no other spots. So this means that I don't actually need my candidates test. I just need to reason a little bit around this one spot, and this is most likely going to be our max fish happening at this time. So to figure out what spot that is, let me do second trace and 0, and let me press enter a little bit to the left of that, and enter again a little bit to the right, enter one more time, and we see that this is going to be a value of about 6.204. So e of t minus L of t equals 0 at, I'm going to rename this as A, 6.204, so that way I don't have to keep writing this number. Sometimes I would store this also as a constant on my calculator. It turns out I don't need to use this value again on the problem, but at the very least I don't have to keep rewriting it. So here's what I notice. I notice that f of t is greater than 0, which is to say the number of fish is increasing on the interval from 0 to a. And I also notice that f of t is less than 0, which means the number of fish is decreasing on the interval from a to 8. So if the number of fish is increasing until we get to time a, and it's decreasing after that, then the greatest number of fish in the lake must occur at time a hours. For the last part of this question, we want to know if the rate of change in the number of fish of the lake is increasing or decreasing at time 5. So this one's a little tricky. First off, remember from part C, we defined the rate of change of number of fish in the lake as E of t minus L of t, and I call that F of t. So F of t refers to the rate at which the number of fish is changing. Now we're asking if this quantity here is increasing or decreasing, which means I'm trying to figure out if f prime is positive or negative. That's really what I'm asking here. And I'm asking specifically what's happening at time 5. So to answer this question, I need to find f prime of 5. And since I've already defined what f is, I can just take the derivative of this at a certain specific value without actually showing what it looks like algebraically. But if I really wanted to, I could say f prime equals e prime of t minus L prime of t. Not necessary, though. So let me plug this in the calculator. So on my calculator, recall in part C, I defined y3 as basically e of t minus L of t. This is my f of t function here in y of 3. So quitting out of there, I'm going to do math 8 to take the derivative of that. I'll put an x down there with the d, and I'm going to do alpha trace y3 in this derivative. And this happens at time 5, so let me put 5 in for there. Press enter. And this comes out to approximately negative 10.723. So because this is a negative number, this tells me that f itself, the rate of change of the number of fish, is decreasing at time 5. For this calculator-based free response, we have during the time interval 0 to 4.5 hours, water flowing into tank A at a rate given by this A of t function right here. And during the same interval, water is flowing into tank B at a B of t rate of liters per hour. We didn't get any information on what B of t looks like, but they're telling us, hey, this is the rate at which water is flowing into tank B. They did, however, actually give us the graph of B of t up here. And we're told that these graphs intersect at t equals k and t equals 2.416. So k, it looks like, just kind of looking at this graph, is pretty close to 1 from the looks of it. So now, how much water will be in tank A at time 4.5? That's the first question we want to answer. So we're told that both tanks are empty at time 0. That's the first important question, is how much water do I have when we start? 0. Okay? So to get the water in tank A at time 4.5, we just have to take the starting amount, which was 0, and add the integral of the rate at which water is going in, the integral of A of t. So we're going to have 0 plus the integral from 0 to 4.5 of A of t dt. And now we can just do this on the calculator. So to make my life a little bit easier, and because I feel like I'm going to have to use this multiple times, I'm entering A of t as y1 and my y equals. Quitting out of there now, I'm going to just do what I did down here. I don't need to bother writing 0. I'll just do math 9 to get my integral. We're going from 0 to 4.5. And that's going to be, let's see here, alpha trace y1. That's the A of t function that I want to take the integral of. And we'll put a dx there. And that's going to equal, drum roll please, we got 66.532. And this is going to be in liters. For this problem, they're telling us during the time interval from 0 to k hours, so that's this interval right here, because this is k, this first intersection, water's flowing into tank B at a constant rate of 20.5 liters per hour. Okay, so they're telling us that B of t, which is the rate of change of the water in tank B, is going to be 20.5 on this little stretch right here. So this is basically a horizontal line until we get to this intersection. So based off that, we want the difference between the amount of water in tank A and the amount of water in tank B at time k. So I essentially want to take an integral of the difference between the rates of b and a. In order to do that, though, an integral requires an interval. We know that this interval is starting at time 0 and ending at time k, but I can't plug k into my calculator until I know what k actually equals. So to figure out k, I'm going to have to basically figure out where one of these functions equals 20.5. Now, the good news is that since we know that this is a height of 20.5, and we know that a and b intersect at this spot, we know that a of t equals 20.5 at this time k. So to find k, I just need to figure out at what time a of t equals 20.5. So let me do that. Let me set a of t equal to 20.5, and I'll solve that on my calculator now. So to make this happen, I'm going back into my y equals. I've already got my a of t function entered as y1. For y2, I'm going to enter the horizontal line y equals 20.5, and then I'm just going to figure out where these two things intersect. And I also need a window for this. I'm just going to set my window to be 0 to 4.5. I could probably set it even smaller because I know that this intersection is around 1, but whatever. Let's do zoom fit, and if I need to zoom in, I will. So here is the graph of A, and here, about to come up here, is the horizontal line 20.5. So this is essentially the graph of B until we get to this intersection point. Let's find out what that intersection point is. That'll be second trace, option 5 for intersect, and then let me arrow closer to that intersection because there's two places this intersects. So we've got, let's see, enter, enter, enter. It gives me a value of about 0.892. So there it is, and I'm going to store that value as k. Now, I already can refer to this as k on paper here, and I'm going to label this as k. So whenever I say k now, I'm talking about this number. But on the calculator, I want to do this as well because I actually need to use this number. So let me quit out of here, and I'm going to press the store button to store the x value I just got as alpha k. All right. So at this point, I just need to take the integral of the difference between b and a until we get to this k value of 0.892. So b is a constant value of 20.5. That's the rate of change of b. It's just this constant value. So we're going to take the integral from 0 to k then of 20.5 minus the a of t function. And I'm going to put a dt in there. So now I just need to do this on the calculator. So let's do math 9 to get my integral. I'm going 0 to k, so alpha, let's see, alpha k, there we go. And then we're going to do 20.5 minus, now I stored a as y1, so let me do alpha trace y1. And then I'll put an x there, press enter. And the difference is going to be about 10.599, and that's in units of liters. For this part of the problem, they're telling us that the area of the region bounded by a of t and b of t between k and 2.416, so basically this area right here, is 14.470. Might be helpful to know. Based on that, how much water is in the tank B at time 2.416? So basically, we're trying to find the area under the curve of b of t from 0 to 2.416. But this is a little tricky because we don't have an exact formula for b of t. We do have a formula for b of t between 0 and k. It's this. It's that 20.5 constant amount that they talked about in part B. We have a formula for a for the entire span of the graph, and a includes the area of b in between k and 2.416, but a also includes some area that we don't want. So we're going to have to split this up into a few pieces. First, let me take care of the area under b between 0 and k. That's just going to be the integral from 0 to k of 20.5 dt. So that takes care of this area. But now we need this other area here. So to get that, I'm going to start with the area that I know, or at least I can find, the area under the a function. So I'm going to get that by adding the integral from k, which I've already got stored from part B, k to 2.416 of a of t dt. But now because that's more than I really wanted, I don't want this area that's bounded between them here, I'm going to turn around and subtract this excess area of 14.470. So if I take the area under A and subtract this area, then on this stretch I'm just going to end up with the area under B between K and 2.416. So let me do all this on the calculator now. So I took the liberty of entering all of this stuff on my calculator off camera. Here's what I entered. I have the integral from 0 to K, and I stored that intersection point as K, of 20.5 dx. And then I'm adding an integral from K to 2.416 of my a of t function, which I stored as y1, so that's what I put in there, alpha trace y1. And then I'm just subtracting that constant amount that they talked about. Let's press enter. And we end up with 48.314. And since we're finding the amount of water in tank B, that's going to be in liters. For the last part on this problem, we're told that during the interval 2.7 to 4.5, the rate of water flow into tank B is modeled by this W of t function. They only want us to find whether the difference WT minus A of t is increasing or decreasing at time 3.5. There's a lot of other things they could ask us to do with this, but really all they want to know is, hey, is this thing going up or going down at time 3.5? Well, to answer that one question, we just need to figure out if the derivative of this difference is positive or negative at 3.5. So that means I need to take the derivative of W of t minus A of t at 3.5. That's going to be W prime of 3.5 minus A prime of 3.5. Now the good news is because I'm only taking the derivative at a single value, and I've already got the original functions A and W clearly defined, they gave it to us, I don't actually have to show what W prime and A prime look like algebraically before I do this plug-in. I can just plug the original functions in my calculator and use the derivative function on there to find these values without showing any further work. So let's go ahead and use that calculator. To make finding the derivative of those functions a little bit easier, I already had A of t entered as y1 on my y equals, but now you'll see down here in y3, I've taken the liberty of entering W of t. So now I can easily plug those into the derivative function without worrying about parentheses or any other craziness. So let me quit out of there, and now I'm going to do math 8 to get my derivative function. I'll do dx, and I'm doing derivative of w first, so this is going to be alpha trace y3 that I'm putting in there. And this is happening at 3.5, so let me put that in my x equals there. Next, I'm going to subtract another math 8 here, another derivative, dx down there. Now I've got the derivative of a of t, so that's alpha trace y1. 3.5 is again the plug-in value for that, and that's coming out to negative 1.143. Now because that is negative, because the derivative of this stuff is negative, that tells me that the original W of t minus A of t is decreasing at time 3.5. On this free response problem, which is a calculator-based one, we have the rate at which cars enter a parking lot modeled by this E of t crazy function here, and the rate at which they're leaving is modeled by a differentiable L function, which they're not actually going to tell us what it is, but they did give us some values of L of t in this table up here. Now these are both measured in cars per hour, and both functions are defined for all values between 0 and 12. Okay, and let's see here. The hours is hours after 5 a.m., which is interesting to know. So now the first thing they want us to do is find the rate of change of E of t at time 7 and then indicate units of measure. So basically we need to do just E prime of 7. And to do E prime of 7, since I've had E defined for me up here, I don't really need to tell you what E prime looks like algebraically. I mean, this would definitely be a huge pain to take the derivative of. So what I can do is just write this original function in my calculator and then use the derivative function on my calculator at specifically 7, give you the answer, and I actually don't have to show any further work once I've shown you that I'm taking the derivative of a function that they already defined at a specific spot. So let's go and do this. So here I am on my calculator in the y equals. even though I don't need to take the derivative of e of t. Entering it sure took a while, but let me get out of there now. And now that I've got e of t entered in y1, I'm just going to do math 8. That pulls up derivative. I'll do dx. For the function I'm taking the derivative of, that's the e of t function that I stored in y1, so alpha trace y1. And then I'm doing this specifically at x equals 7, which is t equals 7 in the problem. So plugging that in, that comes out to about 6.165. And what did we just actually do? What are the units of measure here? Well, e of t itself was the rate at which cars were entering the parking lot. And this was measured in, they said, cars per hour. So if I take the derivative of cars per hour with respect to time, I'm basically dividing cars per hour by hours. So that's going to give me cars per hour, or just simply cars per hour squared. For this part of the problem, they want to know how many cars enter the parking lot from time 0 to time 12, round to the nearest whole number. So the good news is we have the rate at which cars are entering the parking lot. So to find the total number that enter, we just have to integrate this rate of change over the interval from 0 to 12. So we're just doing integral from 0 to 12 of e of t dt. That is all we have to do here. Since e of t is already defined, I can just do this whole thing on the calculator once I've written down what I'm about to do. So let's do that now. And here's what this looks like on my calculator. Math 9 gave me the integral. I did that 0 to 12. y1, again, that's where I stored e of t on my calculator. And dx, press enter. And this is going to be, if we round it off to the nearest whole number, this is going to be 520 cars. On this part of the problem, they're telling us to use a trapezoidal sum with 4 subintervals with the table here to figure out an approximation for integral from 2 to 12 of L of t dt. And if you think about it, this is really the only way we can talk about this cars leaving function using approximations with the table, because we don't know exactly what L of t is function-wise. So I'm going to write that this integral is approximately equal to the following. So I'm going to have 4 trapezoid areas added together, each with a format of base 1 plus base 2 over 2 times a height. So for my first trapezoid, I've got a base of 15 plus 40 over 2 times a height of 3 between 2 and 5. Then I've got a base of 40 plus 24 over 2 times a height of 4. Next, 24 plus 68 over 2 times a height of 2. And finally, we have 68 plus 18 over 2 times a height of just 1. Now, I don't actually have to simplify this, but I'm going to. But if you didn't want to simplify it, you could just put units on the end. Since you're integrating cars per hour, you're basically multiplying cars per hour by hours and getting rid of the hours and ending up with cars for your units. You're basically figuring out how many cars left. Let me just get a number for that, because I do have a calculator to use. So I took some time off camera just to enter all of this in my calculator. I think, honestly, I just like using the fancy fraction mode when you do alpha y equals and do the n over d mode. It's kind of fun. So all of that comes out to, well, that fraction number. Let me do math decimal and convert that into a decimal. So that's 345.5, and I'm not going to round it because they didn't tell me to round it. So if they don't tell you to round it, you've got to be accurate out to 3 decimals if there are any. So that's going to be in units of cars. Now, what did we just find? We just figured out, since we integrated the rate of leaving function, we just figured out the number of cars that leave the parking lot in units of cars from time 2 to time 12. Now, since the t really just tells us how long after 5 a.m. it's been, if we wanted to be real fancy here, we could write from 7 a.m. to 5 p.m. For this last part of the problem, they're telling us from time 0 to 6, $5 are collected from each car entering, and time 6 to 12, the price goes up to 8. We want to know how much money is collected from cars entering between times 0 and 12. So in general, if you want to know how much money is collected, you need the price per car times the number of cars. To get the number of cars that enter, we can just take the integral of this e of t function like we did on some of the problem parts earlier. The trouble on this one is that we have different prices for different times. So that means we're going to have different integrals for those times. So to get the price, to get all the money collected from people between times 0 and 6, I'm going to need my $5 times the integral from 0 to 6 of e of t dt. Now to this, I'm going to add some more money. That's the money collected from 6 to 12. That's going to be $8 times the integral from 6 to 12 of e of t dt. And all of this now is just going to happen on the calculator. All right, so here's everything I entered on the calculator. There's my second money integral. Here's my first integral. Press enter, let the calculator do the heavy lifting. And that's going to be, let's see, they wanted it to the nearest whole dollar. So that's going to be $3,530. Don't spend it all in one place.